Welcome to this tutorial. In this tutorial, we look into Aspen simulation of a regenerative ideal Rankine cycle with an open feedwater heater. In the regenerative ideal Rankine cycle, steam is extracted from the turbine at one or more stages and used to preheat the feedwater before it enters the boiler. This process reduces the energy required by the boiler and thereby improves the overall efficiency of the cycle. By heating the feedwater using steam from the turbine, less fuel is needed to achieve the desired steam condition, which makes the cycle more energy efficient. Uh, Advantages of using heat regeneration are improving the cycle efficiency. By using the heat from the steam to preheat the feedwater, the need for additional energy input in the boiler is reduced. This improves the cycle overall efficiency. We also have another advantage in regard to the aeration of the feedwater. The feedwater heater serves as a convenient means of deaerating the feedwater, preventing oxygen buildup that could lead to corrosion in the boiler. It also controls the steam flow. It helps in controlling the large volume flow rate of steam at the final stages of the turbine, ensuring better performance and preventing excess pressure that could damage the turbine. This approach makes the regenerative cycle a crucial improvement over the standard Rankine cycle, enhancing both efficiency and operational longevity. In the regenerative cycle with open feedwater heater, the feedwater functions as a mixing chamber. The steam is extracted from the turbine. This is a schematic of a simple ideal Rankine cycle with one open feedwater heater. We extract some steam from the turbine. It enters the open feedwater heater and is mixed with the feedwater that comes from the condenser. And since the pressure of the extraction is higher than condenser, we need an extra pump here in order to transfer the open feedwater heater output back to the boiler. If you look into the TS diagram, you see that the TS diagram looks different from the ideal Rankine cycle. Here, from if you look into stream number 2, you see the temperature rises from 2 to 3, and then the pressure increases from 3 to 4 to the same pressure of the boiler. And then you have this constant pressure line. Uh, Ideally, the mixture leaves the open feedwater heater as a saturated liquid at the heater pressure or extraction pressure, which means that point 3 is on this curve in the uh, between compressed liquid area and saturated mixture area. Let's look into this example. Consider a steam power plant operating on ideal regenerative Rankine cycle with one open feedwater heater. Uh, the steam enters the turbine at 15 megapascal, so stream number 5 has a pressure of 15 megapascal and temperature of 600 degrees C. After the turbine, the mixture of liquid and vapor goes to the condenser with a pressure of 10 kilopascal. Let's assume that we extract 20% of the steam and add it to this open feedwater heater. The pressure of this extraction stream is 1.2 megapascal, and we want to determine the thermal efficiency of the steam. This steam that is extracted, stream number 6, is mixed with the feedwater that comes from pump number 2, and it comes from the condenser. Let's see how we can do this in the Aspen program. To start the simulation, we work on a previous file that we did together. Please refer to video part 2, setting of a simple ideal Rankine cycle. add the components that you need: turbine, condenser, pump, and boiler, and then connect them, connect the streams and rename them in the proper way. Now we want to add our feedwater heater, open feedwater heater. In order to do that, we can use a mixer. Could be the simple triangle mixer or a tank. I use a tank, it doesn't matter. Please note that here we just concerned about energy and mass balances, and we do not do like a detailed simulation, so it's not important, I mean, what type of equipment you choose here. The next issue is that we cannot have more than one output for the turbine, which means that if you want to extract some steam from the turbine, we need to do a trick, and that trick is adding an extra turbine. So in order to simulate this extraction, we add one more turbine, but please note that extra turbine plus this turbine is both of them, basically they are in reality one turbine, not two turbines. We just do this trick to do our mass and energy balances in Aspen. I will pause the video. I will add this extra blocks and we'll connect the streams and rename them in the proper way, and then we take it from there. In order to remove some steam from the turbine, we can also use FS split. So we make one FS split after the first turbine, and then we add the second turbine and the um, open feedwater heater or a tank right after the uh, uh, first pump. And then you also need one more pump after the open feedwater heater, because you need to increase the pressure in two stages. Please note here that if you look into the temperature changes, before the turbine is 600, then it goes to 46, and after the pump 51, and then goes to the boiler. The temperature rises from 51 to 600 in the boiler. And the calculator, if you remember, we did some calculate. We added the calculator to calculate the thermal efficiency of the cycle. If we look into the result, the efficiency of this cycle was 30.4%. Now we add these extra components, and then we continue from there. Okay, as you can see now, I have added one extra turbine. I added one splitter to remove some part of the steam after the first turbine as extraction and send it to open feedwater heater. I use a tank here, and also I added one pump. Now all the components are added. We need to start and add information needed for the program in order to perform the simulation. If you click on next, we are navigated to pump 1. If you check the pump 1 is after the condenser. We said that the pressure of the open feedwater heater is 1.2 because it's the same pressure as the extraction. So pump 1 discharge pressure should be 1.2 megapascal. Next is pump 2. Pump 2 goes to the boiler, so we need to add the pressure of the boiler to this pump. We go back to pump 2, discharge pressure 15 megapascal. If you have efficiencies for driver and pump, you add it here. Next is the block splitter. We need to specify how much do we want to extract or extract from the turbine to send to the open feedwater heater. According to the example, we need to extract 20% of the steam. So in the splitter, we have two streams, turbine 2 in and extraction. So we specify the value of 0.2 to the extraction. We click on next. Next is turbine 1. The discharge pressure of the turbine 1 should be equal to the pressure of the open feedwater heater and the extraction. So the pressure here, here, and here is the same. So turbine 1 discharge pressure is 1.2 megapascal. Uh, then we go to turbine 2, discharge pressure was 10 kilopascal. And then we have all the information needed for the simulation. We also had a calculator in the previous calculation, if you remember. Now I have added also the extra parameter to the calculator options. So if you go to flow sheeting option, calculator 1, input, in the simple ideal Rankine cycle, we had a 1 work for the turbine. Now, since we have added 1 extra turbine, we need to count for the work produced in the second turbine as well, and also the work that is consumed in the second pump. And all those are added in the input list here. So work of turbine 1, work of turbine 2, work of the pump 1, work of the pump 2, and Q in is the heat in the boiler. All of them are import variables, so you need to make sure that you have the right uh, option here. So all of them are import variable. And finally, the efficiency export variable, and everything looks fine. In the calculate, I also modified the equation here. The work of the turbine 1, work of the turbine 2, minus the work of the pump 1 and work pump 2. Multiply by 100 divided by Q in. And the sequence, we also check that. So import variable, it reads all these values and then export to efficiency. Everything looks fine. We reset the calculations and then we run it. Okay, we have no errors or warnings. It looks fine now. We go back to the main flow sheet to check all the values for temperature and pressure. I have checked these boxes so we can see the temperature, pressure, vapor fraction, and heat and work. There is a guide over here for you, so please check that as well. So this shows temperature, this one, the signs here. One thing you need to note is that the Q that you see in the boiler and in the condenser, the units is calorie per second, but the units for the pump and turbine is in kilowatts. So let's review the whole process one more time. We start from the turbine, temperature, pressure given. Temperature goes down to 306 at 1.2 megapascal. We remove some part of the steam and send it to open feedwater heater. The rest goes to the second turbine. Temperature after the second turbine goes to 46, and after the condenser is the same because we assume that it's saturated liquid here. Then we have the first pump. We increase the pressure to 1.2 megapascal or 12 bar. And after that, it goes to open feedwater heater. You can see that the temperature now rises to 181 from 46. So the feedwater temperature increases in 2 steps, once here and second here. The temperature rises a little bit further after the second pump, and then it goes to the boiler and gives us the same pressure and temperature of the boiler. So the calculator, let's check the results of our calculator now. We go to the tab for defined variables. Now we see the efficiency increased around 4%. It was 30.4 in the beginning, now it's 34.4. So 4% increase by adding this open feedwater heater, which is very important when it comes to the cost and fuel cost and the overall efficiency of the cycle. Thank you for watching this video. We continue in another video with more similar simulation for this ideal Rankine cycle.